we're gonna do a little bit of freestyle exploring today. So what I wanted to explore is a little bit the concept of the three dimensionality of quantum programming in the sense and qubits, right? Because it's at the end of the day, after the stuff that I've been going through, that's kind of where it all seems to go. Um, and so I'm trying to move away from the low level stuff and to kind of get into what are the sort of intermediate level concepts that we can explore to really discover what is actually quantum programming, right? And then um, because I think it's a mistake that we should avoid is to try to build that up as like using traditional programming as an analogy, because I think that's something completely different in that sense. So let's see because what I find really helpful in here is that you have like sort of an overview of what all the gates do, and I think that's super useful. I'm missing kind of like having in some sort of like maybe the block sphere visualization helps to understand this three dimensionality. Let me just, if I take a look to the block sphere, that's basically what we have, right? So the z, the x, and the y, and so basically whether that's a accurate or good representation of a qubit or not, it's a different story. Like the thing is, it just helps you understand what is the operational scope of a qubit, but when it comes to then entanglement, it just you can't just do that with a block sphere alone. So you can't just have two block spheres and that's it. um, there's a bit more to that, and so some interesting stuff in here I see. Phasing, dephasing, whatever. Um, so so I think that's an interesting concept. So I don't know. Let's play around with this a little bit. What we know is, and again, as I said, like, I'm not gonna get into like how do we measure stuff or not, like what are the measurements across the different axes or whatever dimensions. For me, it all comes down to you do stuff, and then you measure on the z. Like let's pick z, and that's it. And then uh, it's understanding the operations you might do before measurement as something that belongs to the measurement. I mean, it's a convention, right? So I'm gonna stick to 2 qubits. Maybe we'll do 3 later, but that's maybe gonna be easier first. And I'm gonna start by what I know already, and I think because 1 qubit is, I would say, in that sense, kind of boring, right? But we could stay with one first, maybe, and then see what happens with visualizations, right? So if you just talk about 1 qubit, then you've got basically those things, right? So it's either 0 or 1. With a Hadamard gate, you kind of like bring the probability into both. It can be both 0 or 1 with the same probability. Um, when you start with a qubit, that's 0, right? Like if you rotate anyhow through the x-axis, that's not gonna really do anything uh, to your probabilities, because it's just the same. Um, so that's one thing to consider if you rotate to the z-axis. If you do on the x-axis, so that's that rotation, and it's being in the sense that the so it's a minus, but I'm assuming that means the complex dimension. So we're basically when we rotate this way, we're getting into the complex numbers and the complex dimension. what if it's like 8 or something like that? Interesting. Ooh. It's pretty interesting because it also affects a little bit. I mean, yeah, the sum of the probabilities must be 1, but at the same time, that's kind of like flagged, so to say. So we just do pi, then it's 1, but flagged. Interesting. Flagged as in like -1. It's an X rotation. Pi. And if I do of p times 2, what? Ooh. Because geometrically that means so what are we doing? Like that and like that. But why is it then suddenly? So the colors here seem to indicate like it's yellow when the negative part is it's sort of like not the not complex component of that. And so interesting. P. And if I do a rotation of, and it's like -1 times p, then it's not negative, but it's still, you're in the complex numbers. Okay, so the sign, forget about that. The color does not reflect the sign in the case of that, because if, exactly. So basically, as you rotate, it's super interesting. So if you, as you rotate, I mean, that's kind of you're rotating less, right? So if I'm like 30, it's kind of like that. So it kind of keeps growing. It keeps growing, right, until it keeps growing until, I think, until you're like p divided by 2, where both have the same probability. Exactly. And then if you go beyond that, so you get into like 1.5, then you start to lose that, and you're kind of going fully to 1. But it's important to know that you're doing, like, the color is important because it's sort of you're basically encoding information into, let's call the, it's like the pink dimension. So you're encoding information in the complex component. Cool. I wonder how I would get the complex component of the zero part of the state. That could be an interesting. So that's what the rotations on the x side do. The rotations on the y side, they basically, so we are not specifying any color. Those are all on the non-complex part. So everything, when you rotate with the, like when you do X rotations, it's where you are getting into the complex realm. The Y rotations are it's sort of the regular stuff, and the Z rotations, to a zero state make nothing, and to a one state make nothing. So the zero, it's like, I think that the Z dimension is what a lot of people call the phase, and that's what you can see kind of popping up yellow here. So if I, but that's a rotation you can only see if you're not like, because if you rotate, sorry, the z-axis. If you rotate the z-axis, you cannot be on the z-axis, because if you're on the z-axis, you're not gonna feel any rotation there, so to say. So let's say you move. Let's say you rotate. You rotate your like y p and a half, right? So that would have the same end effect like a Hadamard gate, but it's not the same type of behavior, right? So if you do twice that, you're not going to, it's not going to have the same effect like the Hadamard, because Hadamard is a bit of a different beast, and you have to understand that at a low level first. But so okay, so if I do that and now I do a Z rotation, now I'm going to see something. Oh, but why is it pink? Why is it pink? Why is it pink? Because I'm in the complex side of things. But if I do a Hadamard and a Z rotation, it's pink. And we do a Y rotation, it's gone. The next rotation, what? Wow. I think we're gonna have to explore that at a more. It's just the space of possibilities is huge, is immense. So so when do I get it yellow? When do I get it yellow? Because it's basically, I cannot do that. When do I get it yellow? I don't know. Hadamard, and if you do like an S, or if you do the Z, now it's yellow. Okay, so it's because it's on the other side. So everything past. So if I I'm trying to make sense out of this. So if I do like a Z rotation of, say, more than p and a half, so it's like p 1.5. Oh, now it's kind of redder. Do pi. Exactly, now it's yellow. So pi divided by 1.2. That should be orange, kind of fairly yellow. That's a pretty cool color coding. So I guess the color coding here is, I could try to reverse engineer that, but I think it's a mixture of the sign and the complex component. So the complex component determines how reddish or how pinkish the color is, and the sign determines how yellowish the thing is. Yellowish. So if it's positive, it's blue. Yeah, that's cool. That's a cool way to visualize stuff. Um, that's a cool way to visualize stuff. Yeah, definitely. And so what's interesting, nevertheless, is what you can do with 2 qubits, right? But I think that's a good primer. So then you can play around with different things in here. Control stuff, this is when you have 2 qubits, but when you have 1 qubit, that's basically what you get, right? So those rotations. Now with these 3 guys, you can do everything. With these 3 rotations, you can do everything with 1 qubit. Absolutely everything. The U1 and U3 things, like U1, U2, U3, this is just like implementation level gates. So you can forget about them. With those 3 gates, these rotations, you can really just move around 1 qubit. As much as you can. Like you can do whatever you want. And then those things are basically specific versions of that, right? So um, an S, it's equivalent to a rotation of like a Z rotation. So an S is 2 S's are equivalent to 1 Z. So if I do that, bam. And if I now do an S and another S, then it's the same. uh, and the transpose is kind of like they go in the opposite direction. So if I do this and then I do this, we're back at square one. So we're back at like as if nothing had happened after the Hadamard. The same in the T. It's you need 4 of those to make a Z. So these are just like, and so you can see how the color is changing. Uh, and how that is changing in we're here at yellow, where it's like fully negative and then there's no complex component. So that's pretty cool. Yeah. So that's basically, and that's how this is color coded. So it's cool. I'm happy that I've done that. I think that plays out really well. Perfect.